Hey, Terry, can you see it?
Yes, we can. Yeah, looks good.
Okay, perfect. Thanks, Terry. Hello, I'm Bill Rounopoulos, Business Development Manager for OEM and Partnerships at Ross Video, where I've been leading our company's efforts to provide open solutions technology based on AES67, Ravenna, and 2110 to OEMs, serving the broadcast and professional audio industry for the last 5 years. Let's start with a bit about remote production to set the stage. It's clearly a hot topic today, and we had a whole day sessions, multiple sessions on this. Companies around the world have raced to maintain their existing workflows with their personnel dispersed in many off-site locations. Remote production is the new normal, and now that we've experienced its potential, it's likely to continue to be a focus in the future. Historically, when we talked about remote production, we were referring to an OB van or outside broadcast van at a specific site like a sports stadium. Boy, do I miss those days. The entire end-to-end production was done in the broadcasting truck. And what we meant by remote is that it was done outside of a traditional studio. Over time, this evolved into REMI, or remote integration, a model which relied on a production control room within a centralized studio to run multiple offsite events. Not only did this allow the scaling up of production workflows, but it substantially reduced the need to send crews to multiple locations, which was not only more efficient, but resulted in significant cost savings. The shock of last year resulted in another big evolution, or perhaps revolution, in remote production, where the previous centralized way of doing things no longer worked, as production professionals were dispersed in many different locations and couldn't work side by side due to physical distancing guidelines. Now there was a need to maintain existing production workflows while allowing producers, operators, talent, hosts to work from anywhere. We all know the story. Companies scrambled to make this work and had to deal with multiple different unknowns, among them bandwidth-constrained environments. While many solutions were hastily cobbled together, a lot of trade-offs were made. There is still a need for higher quality productions with lower latency that integrate easily with existing equipment. This is where AES67 and transporting it over the WAN comes in. Just before the holidays, at the end of last year, a group of us, AES67 Ravenna partners, got together on an intercontinental AES67 over WAN demo utilizing the public cloud. This was an outgrowth of several experiments that we performed at Ross in North America with our equipment, involving large but modest distances of 500 kilometers or so, which included not only transport, but some audio processing in the cloud as well. A lot of effort, planning, and coordination went into this global proof of concept. It involved equipment from 3 companies across 4 different sites over 2 continents, and leveraged the public cloud infrastructure from Amazon Web Services, including the public internet. I know some of you are anxious to jump into the proof of concept results, but before we do that, I would like to review our goals and objectives for this effort and provide some background on the challenges, which I'll follow with a quick description of the setup and equipment at each site. Then we'll look at the demo results and a summary of what we learned. And finally, we'll wrap up with an outline of topics for future study and Q&A. Let's start with the why. Why did we bother with these AES67 over WAN experiments? The basic question is, why did we bother? We wanted to understand if we could send AES6 traffic over the public infrastructure and the cloud. The basic question is, can we do it? And can we do it across long distances? Even if we can, are we able to listen to something resembling audio? Would it be good quality? It is one thing for a single company to do it with their own equipment, like we did at Ross in North America, but could we interoperate with equipment from other companies, which is the whole point behind AES67? Finally, how could we do it? What challenges would we face? These were the questions. First, some background. AES67 uses IP, but it was designed with local area networks in mind that are synchronized to PTP. Packet loss is not an issue in the LAN and wasn't considered as part of the AES67 standard. In other words, AES67 doesn't work if packets are dropped, which happens and can be quite frequent at times in the public network. Having said that, AES67 and Ravenna have been proven and are being used in WAN applications across private networks, even though WAN applications were not contemplated by the standards. Private dedicated networks, whether owned or leased, are architected well and come with performance guarantees. This is not the case for public networks. Public networks are the equivalent of the Wild West. You never know what you're going to get, and you can't control them. They are congested and unpredictable. They don't use PTP-aware switches, and there are no quality of service guarantees. Public networks suffer from packet loss due to link failures and have large, sometimes dramatic delays due to packet retransmissions. The public network is indeed a very harsh environment for AES67. Let's examine the three main challenges. Increased latency and packet jitter is definitely a problem. Drop packets, as we've discussed, how do we deal with them? And timing and synchronization, which is always a challenge, but more so in this situation. Now let's go into a bit more detail on each one of these. The increased latency and packet jitter would normally be a massive challenge. Ravenna receivers and some AES67 ones handle this by design with large buffers. These, along with other techniques leveraging those receiver buffers, can compensate for the added delay. Ravenna requires receiver buffers to handle at least 20 milliseconds of latency, while AES67 specifies a minimum of 3 milliseconds, but recommends 20. Well-designed AES67 solutions, like all the equipment used in this demo, come with even larger buffers and can handle much more latency. An AES67 standard working group has been formed that is focused on the use of AES67 in WAN applications, and one of its key recommendations is to increase the minimum buffer size in AES67 solutions. In summary, the increased latency of the public network is not an issue for Ravenna or well-architected AES67 solutions that have adopted the standards optional recommendations for larger receiver buffers. Next challenge, as we just said, packet loss. This is an important one. Ravenna and AES67 are not designed to work with drop packets, as mentioned earlier. Fortunately, there are other transport protocols that are architected to deal with drop packets without introducing a lot of extra latency. These were mainly designed for video, but can work with audio as well. Examples of the most popular ones are SRT, Zixi, and lately RIST. In this demo, we solve packet loss by encapsulating AES67 traffic within SRT. Some may cry foul here and claim that we're not actually transporting AES67 if we are using SRT. But you can think of SRT as just a wrapper, and in no way does it alter the AES67 packets. The audio is still transported end-to-end as AES67. The final but significant challenge is timing and synchronization, which is key to AES67 and Ravenna. We start by having a separate PTP grandmaster at each site that is synchronized to GPS. All the equipment at each location is locked to PTP locally. No PTP packets are sent across the WAN or through the cloud. This is not currently practical as packet jitter is too high. Instead, we leverage AWS's time sync service, which uses Crony, which is also locked to GPS. Since the PTP grandmaster at each location and AWS are GPS locked, we can maintain synchronization across the WAN. This is how we attempt to solve this challenge. Now let's take a quick look at the equipment and setup. First, let's explore the setup in North America at Ross Video. In our Ottawa area labs, we generated AES67 sources from 2 different platforms, each in separate physical locations that were a few kilometers apart. In our main site, we used our SoftGear COTS-based microservices platform. SoftGear is very handy for these demos as it gives you the flexibility to quickly adapt to changing workflows on the spot. Our SoftGear platform transmitted the AES67 streams to an external SRT gateway where the stream was wrapped into an SRT flow, and then sent via the internet to the AWS cloud by Virginia. At the same time, the SRT flows from Europe were received from the cloud, and the AES67 streams from the SRT gateway were sent to the SoftGear platform, and were also transported to our nearby Canada lab via the Ross local area network, where they were received by IGI, our compact audio over IP bridge product. The SRT gateway consisted of a Linux server running Haivision's open source implementation. Setting up the SRT gateway is very easy to do and very quick, taking even first-time users 45 minutes or less. In this case, we decided at Ross to use an external gateway. In past demos, the functionality was integrated into our software platform. For synchronization, we connected all the Ross AES67 equipment to a PTP Grandmaster that is locked to GPS. Although we have only focused on transport in this webinar, we did run a successful experiment at Ross, which also included processing in the cloud. In that case, we sent AES67 streams to AWS, processed the audio using a Nielsen watermarking and coding application that we ran in the cloud, and sent the AES67 streams back to our lab. Here are some screenshots of the configuration and setup of the Ross video equipment from the live demo. Both Softgear and IGI use our standard dashboard controller, tailored with custom panels to fit the needs of each product. As this demo used equipment from 3 different AES67 suppliers, we will be showing screenshots from them as well. Now, turning our attention to Europe. We start with the setup at Merging Technologies, which involve 2 locations, Merging headquarters in Lausanne, Switzerland, and 200 kilometers away in Grenoble, France, where Nicolas Turmel, who was a speaker earlier today, was located and put together their part of this global demo. The Grenoble location used Merging's audio device, a virtual sound card, to generate and receive the AES67 streams. Merging's audio device supports multi-ASIO clients for the recording industry. At the Lausanne site, an Anubis was used, Merging's compact A to D, D to A interface with a fully featured monitor controller that integrates well with digital audio workstations. In this setup, the SRT was hosted on a separate external gateway connected to AWS in Frankfurt. Merging used a SoundFX Grandmaster locked to GPS to synchronize all their equipment to PTP. The setup and user interface for Merging's audio device software and Anubis are shown in these screenshots taken from the demo. In the Anubis display, the SDP or Session Description Protocol settings and the playout delay are displayed. The SDP settings were configured manually and were the same for all the equipment in this proof of concept. Turning to Mittweida, Germany, and direct out setup, it was put together by Claudia Becker-Foss, who presented just before this webinar. Direct out used their Prodigy modular audio converter with the RAV2 AES67 Ravenna card to generate and receive the AES67 streams. Direct out incorporated the SRT gateway functionality into their Prodigy converter, which communicated directly over the public internet with AWS in Frankfurt. One novel piece of their setup is that Direct Out used an inexpensive PTP Grandmaster based on a Raspberry Pi that was tied to GPS. A very handy solution in the field that gets the job done when a full-blown Grandmaster is not available. Here are 2 screenshots from the Prodigy user interface, which highlights the network offset or delay of the received stream from Ross in Canada and the one from Merging in Switzerland. As expected, the received stream from Ottawa, originating from much farther away, has a higher network delay. We have shown multiple screenshots of different controllers and customized user interface from several companies supporting AES67 Ravenna that participated in this proof of concept. As an aside, this shows the power of innovation driven by open standards like AES67. Different equipment ranging from a virtual sound card, a COTS-based platform, compact and modular audio converters to an audio D to A to D solution for the recording industry, built by different companies, all connected together as envisioned and enabled by AES67. Now, before going to the results of the demo and discussing what we learned, I want to zoom out again to the big picture and block diagram architecture of the demo, as summarized in this graphic created by my Ross Video colleague, Angelo Santos. On-site in Ottawa, Mittweida, Lausanne, Grenoble, various pieces of AES67 equipment from Ross, Direct Out, and Merging were used to create and receive AES67 streams. Gateways, integrated or external, at each local area network wrap these streams into SRT flows using Haivision's open source SRT implementation, which were then sent to the nearest AWS cloud access points using the public internet. The flows were then transported over the AWS cloud infrastructure between the access points, from where the secure SRT flows were then handed off to the local SRT gateways over the public internet again. The gateways unwrap the AES67 streams at each location, at each local site, so they could be received by the AES67 devices. All the AES67 equipment were locally locked to P2P Grandmaster at each site, which in turn were synchronized to GPS. This ensured that all AES67 devices were synchronized to the same time source, allowing the generated streams to receive the exact RTP timestamps, which were then transported transparently through the cloud. This provided deterministic and stable playout latency, allowing the receiving endpoints to be configured to compensate for the delay and to align the incoming streams. Since the streams were not modified or altered in the cloud or by the SRT gateways, the audio data was transparently sent from the source to the destination, uncompressed and at full quality, as expected. To help visualize what was happening during the demo, Nicholas Termel established a local loopback server hosted on AWS to monitor the streams. He also created a monitoring app to analyze the AWS packets and this web page that you see to display the results. This allowed any participant during the demo presentation to listen in on the live streams via an HTTP link within a web browser. Users could click on any individual stream to listen to the audio being received at that location. The web page included live volume unit meters, along with network delay and accumulated packet loss statistics per stream at each site. We kept all the equipment up and running along with the website for another 15 days after the live proof of concept presentation and advertised it on the Ravenna site to allow anybody to easily access it and experience it at any time during that period. Now we will review some results and what we learned. First, we can send AES67 over the public WAN utilized in the cloud. That's awesome. We were very excited about that, and it literally worked right out of the gate. Local only P2P synchronization and AWS locked to GPS works just fine. Packet loss was handled well by the SRT protocol. However, due to the occasional packet retransmission, the receivers had to be configured to handle more latency to manage the larger packet delay variation. Connections were set up manually. Latency, which ranged from 200 to 600 milliseconds, is lower than what we anticipated, but still significant and heavily dependent on the quality and bandwidth of the local internet connection used to get to the cloud. It's important to use the closest cloud access point possible. We tried a last-minute attempt to connect to ROS equipment in Brazil. The AES67 Brazil streams were accidentally sent to AWS in Virginia via the internet instead of using a local access point in Sao Paulo. Amazingly, the audio was still playable, but not high quality, as it was mostly transported over the best effort internet instead of the cloud. In addition, to manage the increased latency, we had to manually tune the link offset at each site, but the deep buffers of the AES67 Ravenna receivers were easily able to handle the network delay. As mentioned, this is a proof of concept demo, and we are very pleased with the results. It required some expertise in fiddling with manual settings to get it to work. There are a few items that require further study to make it a more practical and usable solution. A big one is how to transport timing through the cloud. Quite a few companies are studying this challenge. Daniel Bolt talked about some of Mindberg's work on this in an earlier webinar today. We consciously decided on manual connections using STP files to keep things simple. It would be very valuable to be able to use NMOS or a vendor registration and discovery to automate the connection process. Ease of use would be greatly enhanced if the link offset could be handled automatically to compensate for the network delay. To manage packet loss, it would be interesting to learn if SMPTE 2022-7 redundancy would work. Although SRT worked great, it would be good to experiment with RISC to understand if there are any performance or reliability benefits. In summary, the proof of concept showed there's a lot of promise for AES67 in the cloud, and we are eager and motivated to tackle these open items in the near future. Thanks for listening. Now it's time to answer any questions.